We are dominated by the very small. We don't even think about it. When we take our phone out of our pocket, we don't think of our phone as being that small, but there are billions of things, of transistors inside your phone. We're used to high tech, always moving smaller, smaller, smaller. But we're running up against some limits, and those limits are that as things get smaller and smaller, the physics that controls how things act, the underlying science, instead of being the old school physics, which is called classical physics, which you can think of as like pool balls rattling around on a table and clacking into each other. As you get very, very small, instead of acting like these little balls, they act more and more like waves. And the underlying physics is not called classical physics, it's now called quantum physics. Where things start getting complicated and harder to understand is when you have collections of atoms or collections of electrons bouncing off each other, passing through each other, on their way through our tiny little transistors to turn on and off the ones and zeros on our tiny computers. These problems are hugely more complex, and so oftentimes we have to do experiments to understand them. That's where the ultra-cold temperatures come in.
If you cool atoms down to some of the coldest temperatures you can imagine, colder than any other place in the natural universe, the atoms are moving very, very slowly. And if you're going to make some measurements about their properties, if they're moving slowly, you can make that measurement a lot more precisely.
If all the atoms in this room right now are moving around at 770 miles per hour, the speeds that the atoms are moving once they're cooled is slower than 1,000th of a mile per hour. A cold atom is a controllable atom. You let them out of the trap and they just float.
We are cooling the atoms down to a fraction of a billionth of a degree above absolute zero. And at temperatures so low, we can easily see these atoms for tens of seconds and study and see their dynamics and how they interact with each other.
To do that, we have to be in space. We have to take quantum matter and quantum technologies into space. And we have to work hard to learn how to use quantum technologies in space. And the Cold Atom Laboratory is the first dedicated laboratory that will allow us to do this sort of work.
These types of experiments are the most challenging tabletop experiments that take place on Earth. So to take this up to the space station is a whole new level where we'll have to operate remotely and have a robust working instrument. The Cold Atom Lab will also allow us to free those type of experiments from the constraints of gravity that plague researchers on the ground. Gravity always drags atoms to the bottom of the traps that we use, and in the Cold Atom Lab, we don't have that problem.
When we discovered Bose-Einstein condensation in 1995, the experiment was complicated and difficult. I would have never imagined that it is possible to do such experiments now on a space station. With Bose-Einstein condensates, we reach nano-Kelvin temperatures, so all the atoms have an extremely low energy. So therefore, going to microgravity eliminates a number of limitations for the experiments.
Ultra cold acts like a magnifying glass. It expands the effects of quantum mechanics. That's really the power of these very low temperatures of the Cold Atom Laboratory, as we can learn about these things as we get colder and colder yet.